Here's some problems from chapter 13 relating to the energy of things in orbit. Orbits and energy. So number 61, at what height above the Earth's surface is the energy required to lift a satellite to that height equal to the energy required for the satellite to be in orbit at that height? Well, let's make a little picture here. Here's the Earth. There's the radius of the Earth. And here's the satellite at height. We'll call it h sub 0. Right? And that'll be that special height where the energy required to lift the satellite from here to here is the same as the energy to have it in orbit, the kinetic energy. Now, how much energy is required to lift it to that? Well, that's change in its gravitational potential energy. So that's U final minus U initial, right? That's how much energy is required to lift it to that height, right? From here to here. So let's see. This U final would be negative. I just put these, sorry, I should have said something about this. These are the two equations that we have for the potential gravitational energy of something. This is not necessarily for orbit. This is always true for any two objects of this separation. That's their gravitational potential energy. And then the kinetic energy that's specifically for something in a circular orbit. So to get it from here to here, we have G M M over, and its final radius would be R, radius of the Earth, plus that height, minus negative G M M over its starting at the just the height of the radius of the Earth. And depending on how we want to deal with this, how much algebra you want to do, you could get a common denominator here and that sort of thing. Let's just try this. That's going to be positive, so I have GMM over RE. That's the positive term there, and then minus this. I'm just doing a little bit of algebra there. So I'm going to leave that like that for now. And then the kinetic energy of orbit is equal to, when it's up there, it'll be GMM over 2 times R. And when it's in orbit at that height, that radius is that. Right? So they want to know when are those two things equal to each other. Right? So let's go ahead and set up that equation. So we have this. Notice that the GMM, I'm going to factor that out of all these because that's going to end up not playing a role here. So GMM factors out of this, and I have 1 over RE minus 1 over RE plus H sub 0 equal to GMM over 1 over 2 RE plus H sub 0. So really boils down to setting these two things equal to each other. So I guess I better get a common denominator. So here, getting that common denominator, I have RE minus, RE plus, sorry, messed that up. Finding a common denominator, RE plus H sub 0 here, minus RE here, over the common denominator, which is RE times RE plus H sub 0, equals 1 over 2 times RE plus H sub 0. And doing some simplifying here, I have this factor on the bottom of both equations, and then RE minus RE on the top. So here I have H sub 0 on the top over RE is equal to 1 over 2, or that the magical height that this happens at is the radius of the Earth over 2. And there you go. Part B is, you got to think about that a little bit, I think. So what happens if we have to lift it to a height that's higher than this? How is that going to affect our answer? So if H sub 0 is greater, then how is that going to affect these two things here? If the H sub 0 is greater than RE over 2, well, if the H sub 0 is greater, that's going to make this fraction smaller, right? That will make this larger, right? And that's going to have a greater effect here than here. So it turns out, and you can try, if you're not convinced by that, you can try plugging in a value of, say, let's say maybe we could try this just real quickly to convince ourselves. So in part B, let's say we lift it to a height of the whole radius of the Earth, right? So let's say we lift it to height of RE above the Earth. Then this expression would become, delta U would become GMM over RE minus GMM over 2RE, right? It would become GMM over RE minus GMM over 2RE. So what we're doing here, this is try for H equals. That's what we're doing here. We're just messing around with that. And common denominator here, I could multiply this fraction by 2, top and bottom. So that would give me GMM over 2RE. And then the kinetic energy at that greater height of the radius of the Earth would be now GMM over 2 times my R is now 2 radiuses of the Earth. And you can see that in this case, when we've gone higher than this H sub 0, this special height when they're the same, again, just recapping what this answer is, that's the special height that requires the same amount of energy to lift to there as the kinetic energy it would take to be in orbit there. So if we go higher than that, then you can see that this is greater. This is only half, and this is a quarter of the same expression. So they, how did they phrase the question? They said, for greater heights, which is greater? So with the greater, delta U is greater. That's probably the best way to do that. Just pick a value and work that out. All right. Use the other half of this page here. Number 62. 2 Earth satellites, A and B, each of mass m, are to be launched into circular orbits about Earth's center. Satellite A is going to orbit at an altitude of, so the altitude of satellite A is 6.37 times 10 to the 6th meters. That's just about the radius of the Earth right there. And the satellite B is going to orbit at an altitude. This is not the radius, this is the altitude, right? So we have to add in the radius of the Earth. of 1.911 times 10 to the 7th meters. When I change that to meters and put it in scientific notation. So the radius of orbit A is this plus the radius of the Earth. And I'm not going to mess around and try to do that without me calculator. So 6.37 is 10 to the 6th. And that is also the radius of the Earth, so I just need to add that in again. And I'm going to go ahead and cheat here and put my calculator in scientific notation mode, which helps me out there. So that radius is 1.27 times 10 to the 7th meters. The radius of B is 1.911 times 10 to the 7th meters, plus the radius of the Earth, which is 6.37 times 10 to the 6th meters. It gives me an orbital radius, in other words, distance from the center of the Earth, of looks about twice that. So whether you notice this or not, you notice I'm going to note that RB is equal to 2 times RA. Looks like that radius is exactly twice this one, so they've set this problem up so that's true. Maybe we can learn something from that. All right, and they want to know what's the ratio of the potential energy of satellite B to that of satellite A in orbit. So I want the ratio of the potential energy of B to the potential energy of A. So that's GMM, negative GMM over R to that of satellite. Oh dear, did I get I got that backwards. Sorry, that's supposed to be B on top. That's 2.55 over GMM over the radius of A. And when I clean this up, cancel, dividing by a fraction, same as multiplying by the reciprocal, that's going to be about 1/2. So noting that that was true, I guess, made that a little bit simpler, right? Part B. What's the ratio of the kinetic energy of satellite B to that of satellite A? The ratio of the kinetic energies now. So kinetic energy of B to kinetic energy of A. So the kinetic energies, we have GMM over 2R, and this is B on top, 2.55 times 10 to the 7th over GMM over 2R, and everything cancels out except for these same two numbers again, dividing by a fraction, same as multiplying by the reciprocal, so that's also 1/2. Right? It just boils down to the ratio of those radii, but they get flipped, right, because they're both on the bottoms of those fractions. Part C. Which satellite has a greater total energy if it has a mass of 14.6 kilograms? And by how much? So the total mechanical energy, remember from our notes that I don't think this is necessarily something you need to remember, but if you add together U plus K for orbit, then you always get negative GMM over 2R. Right? Those expressions are very similar for potential and kinetic energy, and if you add them together, you always get negative GMM over 2R. So what's the difference between satellite A and B? So the total mechanical energy, let's do it this way, for A is negative GMM over 2, it's radius of A, and we're going to actually calculate that. So that's negative G times the mass of the Earth times the mass, what is it, 14.6? 14.6 over 2 times the radius of A is 1.27, it's 10 to the 7th. Oops, I forgot a multiplication sign, didn't I? So let's insert that there. I think that's good. And GMR, that is negative 2.44 times 10 to the negative 10th joules. But I don't like that answer. I don't like that answer because of that negative exponent there. So, why? Oh, I know why. Sorry. I used the, let me go back and get that. I used the radius of the Earth here. That's supposed to be the mass of the Earth. That's my problem there. This should be 5.98 times 10 to the 24th. Right, not the radius of the Earth. Sorry about that. So that changes that quite a bit. It's negative 2.29 times 10 to the positive 8th. Sorry about that. It's definitely, I'll pretend this is a teaching moment and just tell you that it's a risk. Not a risk. I guess it's just something that's built into these problems when we're dealing with all of these really large numbers, that there's a little bit of disorientation that happens. So, sorry about that. Let's see if we can do a better job this time. And this time I just have to fill in the radius of B, so I'm going to go back and pick that same thing up and change that to 2.55. That gives me here negative 1.14, not surprisingly. See the 2 to 1 ratio there? Times 10 to the 8th joules. Right? And what's the difference between these? The difference is that this one is bigger, right? It's a smaller negative number. So the mechanical energy of satellite B, which is at a greater radius, right, higher up, is greater. Let's say, greater. And you can do the math here and subtract them, but it's greater by that 1.14 or 1.145, something like that, times 10 to the 8th joules. It's greater by that much. And part D by, oh, I guess that is part D. By how much? There you go. There's 62. So there's definitely some, nasty number crunching involved in these problems. I can't really avoid that. Number 63. An asteroid whose mass is 2 times 10 to the negative fourth times the mass of the Earth. So the mass of this asteroid is 2 times 10 to the negative fourth times the mass of the Earth. And if you want to actually calculate that, we can do that easily enough. So 2 times 10 to the negative fourth times the mass of the Earth, which is 5.98 times 10 to the 24th. So the mass of our asteroid is let's say 1.2 times 10 to the 21st kilograms. It revolves in a circular orbit around the Sun at a distance that's twice the Earth's radius from the Sun, twice the Earth's distance from the Sun. Calculate the period of revolution of the asteroid in years. A couple ways to do this. We know that Kepler's third law says that period squared is equal to 4 pi squared over gm times r cubed. So you could think about what happens when you double this distance. What happens to this? Well, if you double this, it goes up by a factor of 8, but this is the square root. So that means that if you double r, that means you increase this by the square root of 8. Right, that's just proportional reasoning. If you double the r, this is an 8 here, but this is a square root. So that means the period is going to increase by the square root of that factor, which is an 8. So it increases by the square root of 8. So you can plug in all the numbers, and there's definitely a way to do this problem just by calculating that way. But I really like this proportional reasoning here. And that means that if I'm doubling r, there's this increase in the time period, and the time period is it's that much times 1 year, right? I'm increasing it from what the period would be from an Earth year. So I get 1 year times the square root of 8, which is the square root of 8 years. I'm sure you celebrated when you turned that age. So about 2.8 years. Again, there's a much longer way of doing that by turning everything into seconds and going through the whole process, but that proportional reasoning I think is very, very powerful and successful here. Part B. What's the ratio of the kinetic energy of the asteroid to the kinetic energy of the Earth? So the kinetic energy of the asteroid to the kinetic energy of the Earth. The asteroid, we've got kinetic energy be G, M, over R, and the R here is 2 astronomical units. You can look that up and put in a number there, but it's 2 times the distance from the sun, from the Earth to the sun, over. Oh, and it's it's 2 times that, right? Because this is the kinetic energy formula, so it's 2 times the distance, and that distance is 2 astronomical units here. Let me just take this moment to remind you that in these videos, if you get to a point where I'm doing something and you're not exactly sure where those numbers are coming from, that's the point where you need to pause and think about, what's going on, what formula is this that I'm using, like where are these numbers coming from, and so on. And then also cross your fingers that I didn't make a mistake, and then fire the video back up. Kinetic energy of the Earth, GMM, the mass of the Earth is 5.98 times 10 to the 24th over 2 times r, and the radius of the Earth going around the Sun is 1 astronomical unit. So I used those because I knew that those were going to just cancel out. I knew that this is just a 2-to-1 ratio of those things. So lots of stuff cancels out here. Dividing by a fraction, same as multiplying by the reciprocal. The GMs cancel out. The AU cancels out. So I end up with, and the 2's, those cancel out also. I end up with 1.2 times 10 to the 21 over that 2, which didn't cancel out, times, and the reciprocal of this, looks like everything here canceled out except for 5.98 times 10 to the 24th. And actually, I know what that's going to be, right? Because they already told me this ratio of the mass of the asteroid to the mass of the Earth, that's this. You can do the division if you want, right? But if you do that division, you're just going to get this number back. And then it's half of that. So it's 1 times 10 to the negative 4th as that ratio. And this ratio stuff is good for us too, I think, to think about ratios of quantities like this and see what cancels out and see what the effect is of increasing one thing or decreasing another. Again, that proportional reasoning there I think was a good thing for us to think about. 64. A satellite orbits a planet of unknown mass in a circle of radius 2 times 10 to the 7th meters. The magnitude of the gravitational force in the satellite from the planet is 80 newtons. What's the kinetic energy of the satellite in this orbit? And what would F be if the orbit radius were increased to 3 times 10 to the 7th? So let's see if we can deal with A first. They want to know what is the kinetic energy? So it might seem like we just don't have enough information here. But let's see. Kinetic energy is equal to G M M over 2R. Right? And what I do know is I do know what the R is. So that's G M M over 4 times 10 to the 7th. But I also know that universal gravitational force is equal to GMM over R squared. And they told me that's 80 newtons. And I know what the R is. So that means that GMM is equal to 80 times R squared. Right? That's what GMM is. And that would be 80, actually, we could try to figure that out without our calculator, but 80 times 2 times 10 to the 7th squared. That's 3.2 times 10 to the 16th. That's what GMM is. So this is equal to 3.2 times 10 to the 16th over 4 times 10 to the 7th. Which is 8 times 10 to the 8th joules. that's a interesting little problem, how we tweaked that, right? And now they want to know, if I increase the r to 3 times 10 to the 7th, then what's the f going to be? What would f be if the orbit radius were increased to 3 times 10 to the 7th? Well, I know it's 80 newtons. None of these things are going to change, right? Those are all constants. So if I increase this from 2 to 3, then this would go from 4 to 9, right? So how do we want, I guess the easiest way of doing this would be to say that this is constant, right? GMM is going, just by tweaking this equation, is going to be equal to r squared times 80 newtons, right? And if, actually, wait, hold on a second. Let me just rethink this here. I'm trying to solve for this. So I know that, yeah, I guess we could do it this way. So that's a given, right? So what happens to this when I increase this to r cubed and this remains constant? So if this goes up to, and didn't I solve for GMM? I did. This is the constant, so yeah, this is going to work just fine. So that's equal to this constant. That's a GMM. So now, if I increase this to, instead of 2 times 10 to the 7th, if my r is now 3 times 10 to the 7th squared, then what's the gravitational force going to be? And I guess I should have just gone from this equation, shouldn't I? This maybe is a little bit roundabout way of doing it. I could have just gone from here, said I know what GMM is, it's this, and then divided by that. So anyway, in a roundabout way, I got back to that same place. So 3.2 times 10 to the 16th divided by 3 times 10 to the 7th squared. And that is 35.5, about 36 newtons. I still have mine in scientific notation, so that's times 10 to the 1st. So about 36 newtons. All right, one more problem. A satellite is in a circular orbit around the Earth of radius r. The area enclosed by the orbit depends on r squared because a equals pi r squared. That makes sense, right? That's kind of like basically like a related rates kind of statement there. Determine how the following properties of the satellite depend on r. How does the period depend on r? How does the kinetic energy depend on r? How does the angular momentum depend on r? And how does the speed depend on r? So in all these cases, we just need a relationship where we have r on the right-hand side. So how does period depend on r? Well, we know from Kepler's law that period squared is equal to g, I always want to put that on the top, 4 pi squared over gm times r cubed. So how does period depend on r? Period is, this is a constant, so we could say directly proportional to, maybe I shouldn't use this symbol. There's a kind of directly proportional to sign. It looks like an alpha, but it's not. It's more like a kind of extended, it's more like an infinity sign with like the little bit, half of that cut off, and it means directly proportional to. But I won't use that because we don't usually use that, sorry, from other math. So t is directly proportional to, if I square root both sides, r to the 3/2. So that's what they mean, like how does one of these things depend on the other? T is directly proportional to r to the 3/2. That's what they're talking about. So if you weren't really clear about what this problem was asking, that's what it's asking. I would pause now, look for other relationships between the things they're talking about in R, and see if you can figure out what the answers would be. Right? So, okay, for B, they want to know how does kinetic energy depend on R? Well, kinetic energy is equal to Gm m over 2r. This is all a constant, so that means it's inversely proportional to r. So I say K is inversely proportional to r. Part C, what about angular momentum? How do you find the angular momentum in a situation like this? Well, you could really you can do it in either of the two ways. You can do it in big L or small l. I think it makes more sense to my mind to think about the satellite as a particle going around the Earth. So I'm going to use small l, and say that its angular momentum would be equal to r times m times v times the sine of theta. But if it's in a circular orbit, that angle is always going to be perpendicular, right? So the angle will always be 90 degrees, I should say, right? They will always be, the r and the v will always be perpendicular to each other. But the problem is I've got two variables here. So what's v equal to? Well, v for something moving in a circle is equal to 2 pi r over t, right? But that also has a variable in it. So let's see. How do we want to get that v out of there? Oh, maybe we need to use this. So if k is also equal to 1/2 mv squared, right? Remember, that's how we got this relationship. So k, oh, I know what we need to do. Here's an easier way to do it. This is the wrong equation to use. Why is it the wrong one? Because it has another variable in it. But if instead I use this one, the square root of gm over r, right? Then that just has constants and r in it. So the angular momentum is equal to r times m times the square root of gm over r. And then if I just take the constants, put those together, then I have r over the square root of r, which is the square root of r, times m to the square root of g, big M. So this is just a constant. So angular momentum is directly proportional to the square root of r. So I could say that L is directly proportional to the square root of r, or r to the 1/2. And then last part, D, what about speed? How does that depend on r? Well, I think we just did that, didn't we? So the speed is equal to the square root of gm over r. This is a constant, so the speed is inversely proportional to the square root of r. And that is a good little bit of reasoning there, looking at different relationships that we know, and one really that we hadn't really quite considered, angular momentum here for a thingy in orbit. Wait, that's a long video. Guess that's a long assignment.